Hello there, Mr. Sutton here with the AB Calculus 6-4 homework solutions on DiffyQ practice. For this problem, f is a function such that f prime equals x times the square root of f of x, and we're given that f of 3 equals 25. For this part, we just want to find f double prime of 3. That's all. How hard could it be, right? So we've got a product rule that we're going to have to use here, since we have an x times this square root function. So for this, I'm going to use my box and ribbon. I've got an x, I've got the square root of f of x, and now I'm going to go ahead and take their derivatives. So that's going to be 1, and I rewrote this with 1/2 to make it a little bit easier for this next step. We've got 1/2 times f of x to the negative 1/2 times f prime of x, because we have a tail there with our chain rule. Now, before I multiply all this out, I'm actually just going to plug in 3 right away, and then I'll put everything back together. So if x equals 3, let's see what all of these boxes come out to. So up here, this is just going to be 3. Here we have f of 3, which is 25, they told us, but now we're square rooting that. So that's actually just going to be 5. Down here, 1 is 1, and we've got 1/2 times the negative square root of this. So basically, 1/2 times the square root of 25, or 1/2 times 5. And don't forget f prime of x. Now, what's f prime of 3 going to be? Well, here's f prime. So if we just plug 3 into this expression, we've got 3 times the square root of f of 3. So that's 3 times the square root of 25. And now just cleaning this up a little bit here, we've got 1/10 over here. This is going to be 3 times 5, so 15. So 15/10, which we could reduce to 3/2. All right, let's go ahead now and do our ribbon. So I've got 1 times 5 plus 3 times 3/2. And if you want to clean this up even more, although there's no need, you don't need to simplify, this would be 5 plus 9/2. So 10/2 plus 9/2 gives us 19/2. For this problem, we want an expression for y equals f of x by solving this differential equation here with the initial condition f of 3 equals 25. And if you look closely at what they're doing here, they just took this thing that they started with and replaced the f of x with a y. So not really different from what we were dealing with before. But since we're doing DiffyQ and we have a y in the differential equation, we're going to have to separate our variables. So I'm going to begin by dividing both sides by the square root of y. If I'm dividing by y to the 1/2, that means I have y to the negative 1/2, along with the dy on the left side. And on the right side, I'm going to multiply the dx, so that's x dx. Anti-differentiating the left side now, this bumps up to a 1/2. Multiplying by the reciprocal of that, we have 2y to the 1/2, or 2 times the square root of y. On the right side, this is going to be 1/2 x squared plus c. Now let me plug in my initial condition. So I've got 2 times 25 to the 1/2, so the square root of 25. And on the right side, I have 1/2 times 3 squared plus c. Well, over here on the left, this is 2 times 5, so 10. On the right, I've got 9/2 plus c. If I subtract 9/2 from 10, which is really 20/2, that leaves me with 11/2 on the left side, so c equals 11/2. Now I'm going to go ahead and plug that back in. So I've got 2y to the 1/2 equals 1/2 x squared plus 11/2. And at this point, I just have to isolate y. Now, before I do anything to both sides, I'm actually going to turn this into one big fraction on the right side, just to make it a little easier to deal with all at once. So I'm going to have x squared plus 11 all over 2. And now, let me isolate y. I'll start by dividing everything by 2. So I'll have y to the 1/2 equals x squared plus 11 over 4, because if I'm dividing by 2, I'm really multiplying by 1/2. And now to get rid of this 1/2 here, I have to square both sides. So that leaves me with y equals x squared plus 11 over 4, the whole thing squared. On this problem, we're starting off with this differential equation up here. And to start off with this part of the problem, we just want the slope field for this thing at these 12 points indicated. So I'm going to start with a table. I'm going from -1 to 1 with x values, and negative 2 to 2 with y values. And you'll note here that we're leaving out the x-axis. There's nothing on there that we are going to bother trying to find. And with good reason, because if you plug something in here, you have a 0 for y, which would give us undefined, and, can't really graph that. All right, so we've got, let's see, I'm going to do this column by column. For this first column, x is negative 1. So right here, if I plug negative 1 in for x, that's going to zero out the numerator, which zeroes out everything because the denominator is never 0. So we're going to have 0, 0, 0, and 0. Next, if x is 0 itself, well, that means we have 1 in the numerator, so it's going to be 1 over whatever these y values are. So 1 over 2, 1 over 1, which is 1, 1 over negative 1 is negative 1, and this is negative 1/2. Next, I'm plugging 1 in for x, so that's going to be 2 over whatever the y value is. So 2 over 2 is 1, 2 over 1 is 2, 2 over negative 1 is negative 2, 2 over negative 2 is negative 1. Now to graph these out, so I've got horizontal lines for this entire first column here, because these are all 0 slopes. Next, I've got 1/2. 1 is going to be a little bit steeper. And now we've got negative 1 and negative 1/2. Over here on the right column, we've got a 1. 2 is a bit steeper. Negative 2 is steep in the other direction. And then negative 1. But before you move on to the next problem, there's one more part. They said, let's see, sketch a slope field, and for negative 1 to 1, sketch the solution curve that passes through the point 0, negative 1. So that's this point right here. We're just going to sketch the curve following the tangent lines that goes through that point, like so. And now we're done with this problem part. For this problem, they're telling us that the slope field we drew in part A was only at 12 points, but it's defined in every point in the xy plane for which y does not equal 0. So based off of that, they want us to describe all the points in the xy plane such that y is not 0, where our derivative equals negative 1. Well, the quickest way to do this is just to take our differential equation here and literally just set it equal to negative 1 and see what happens. So we can say x plus 1 over y equals negative 1. And there isn't really anywhere to go from here because they didn't tell us too much else about x and y. We could multiply y by both sides to get negative y. And then if we wanted, we could essentially add the y over here, subtract everything else over to the other side. And now we have the equation of a line, y equals negative x minus 1. So all the points on this line, such that y does not equal 0, those are the points for which your derivative is going to be negative 1. On this part of the problem, they want us to find our particular solution to this differential equation, given that we have an initial condition of f of 0 equals negative 2. Because I have y in the differential equation, an output variable here, I need to separate the variables. I'll start by multiplying y to the other side, so I've got y dy equals, and I'll move dx over to the right side, so that's x plus 1 quantity times dx. Next, for my antiderivatives, I've got 1/2 y squared on the left side, and on the right side, this is going to be 1/2 x squared plus x plus c. Now to plug in my initial condition, I'm plugging negative 2 in for the y value over on the left. On the right side, I get 0 for x. So on the left side here, this is half of 4, which is 2. On the right side, everything zeroes out except for c. So then c equals 2, and we can now go ahead and plug that back into the general solution. So plugging that back in, all I have to do at this point is isolate y. I can start by multiplying everything by 2. That's x squared plus 2x plus 4 on the right side. And then I'm going to square root both sides. Before I do that, though, I need to know if I am taking the positive or the negative root of all the stuff on the right side. So looking at my initial condition, I see that y is initially negative 2, which means that in general, y has to be negative, which means that when I take the square root of this equation, I have to take the negative root as my only solution for that right side. So I'm going to write then y equals negative square root of x squared plus 2x plus 4. For this problem, we've got this differential equation with a squared and a cosine piece to it, which is kind of interesting. we want to sketch the slope field for this thing using these 9 points here. So I'm going to set up a table with x values ranging from -1 to 1 and actually y values in the same dimensions. So let me do my columns here. If x is -1, then I've got cosine of negative pi, which is essentially cosine of 180, which is all -1. So I'm going to have -1 times whatever I get for this squared expression when I plug in these y values. So this first y value, we've got y, or 1 minus 1, which is just 0. And then we've got, let's see, this is going to be positive 1 times -1, so that's -1 overall. And then if I plug in -1 for y, that's going to be, let's see, -2 squared is 4, times -1 is -4. Next, if I plug in 0 for the x values, I'm doing cosine of 0, which is going to be positive 1. So y is going to have complete control over what all this comes out to. So if I've got 1 minus 1, again, that's going to be 0. The next one's going to be 0, too, over in this row here. Now if I plug in 0, I've got -1 squared, which is 1. Plugging in -1, I've got -2 squared, which is 4. And then finally, plugging 1 in for the x value here, that gives me cosine of pi, which is really the same thing as cosine of negative pi. So I'm just going to repeat this first column. So 0, -1, and -4. Over here then we have a horizontal line for that top corner, and then this is -1 for our slope, and even steeper, -4. Next we've got 0, +1, and +4. And then this last column is just a complete repeat of our first column, so 0, -1, and -4. On this problem part, they're telling us there's a horizontal line that y equals c that satisfies this differential equation. We want to find the value of c. So let's see, if we have a horizontal line, that means it must have a slope of 0. So that means this whole dy over dx has to equal 0 for this thing to actually be a horizontal line. Okay, well that means that y minus 1 squared could equal 0, in which case y would have to have a value of 1. So we could say y equals 1 is our horizontal line. So then c would equal 1. Now the other possibility up here is that cosine of pi x equals 0. But this is only going to talk about an x value. It's not really going to tell us what y equals. So we don't really consider that part of our equation. For this problem, we're trying to find the particular solution to this differential equation, given the initial condition f of 1 equals 0. So let's start by separating our variables, because we have an output variable, y, in the differential equation. So I'll start by dividing everything by y minus 1 squared. That gives me y minus 1 to the -2 dy on the left side. And we've got cosine pi x dx, if we multiply the dx over there, on the right side. Okay, let's take some antiderivatives. On the left side, this bumps up to a -1. Dividing by that, I've got negative parentheses y minus 1 to the -1. On the right side, antiderivative of cosine is sine, but we have to divide by pi because of that inner function. So 1 over pi sine of pi x plus c. Now we have to plug in that initial condition. I've got 0 going in for the y over here, and 1 going in for the x. Sine of pi is going to be 0, so we've just got c when all is said and done on the right side. On the left side, this is, let's see, -1. The reciprocal is still -1, but we have a negative out there, so altogether +1 for that c value. So let's plug that 1 back in for c in the general solution. Now we have to isolate y. Before I do that, I'm going to merge things together into one big fraction on the right side. So this is going to be sine of pi x plus pi all over pi, if I get that common denominator. And now I can more easily treat this whole right side as a unit when I do things on the left side here. So I'm going to start by negating both sides to get rid of that negative on the left. So I've got y minus 1 to the -1 equals negative all of this stuff in the fraction. Next, to get rid of this -1, I'm going to take the reciprocal of both sides. So that leaves me with y minus 1 on the left and all this stuff upside down on the right side. And then finally, let's add 1 over there. So when all is said and done, I can write 1 minus pi over sine pi x plus pi. And let's call it a day.